Hello all, in this video we will try to understand what is a fixed point iteration method. Firstly, understanding what is a fixed point. A fixed point for a function is a number at which the value of the function does not change. That is, the number p is a fixed point of a given function g if g of p is again p. For example, x is equals to 0 is the fixed point of g of x is equals to x minus sin x. Let us consider an example which says to determine any fixed point of function g of x is equals to x square minus 2. If p be my fixed point of the given function g of x, implies it is in the form of g of p is equals to p, implies p square minus 2 is equals to p, implies p square minus p minus 2 is equals to 0. Now this is a quadratic equation and we know that this quadratic equation has roots minus 1 and plus 2. Here p is equals to minus 1 and 2 are two fixed points of the given function g of x. Geometrically saying, a fixed point of the function g occurs precisely when the graph of y is equals to g of x intersects the graph of y is equals to x. Let us see the graph of this equation. The graph of g of x equals to yb, y is equals to x square minus 2, which is a parabola, and y is equals to x line cut the graph of x square minus 2 at precisely 2 points, which is minus 1 and 2. So these points become the fixed points of the given function. Let us move to the definition of fixed point iteration method. In numerical analysis, we are trying to find the root of an equation f of x equals to 0. This method says to rewrite the given equation f of x equals to 0 in the form x is equals to g of x in such a way that any solution of f of x, which is a fixed point of g of x, is a solution of equation f of x equals to 0. While solving, we start from any initial guess and consider the iterative process. As xn plus 1 is equals to g of xn, where the value of n will be initialized from 0 and will increase gradually. If the given function f is continuous, and the sequence of elements of xn converges to some point p, then it is clear that p is fixed point of the function g, and hence is a solution of f of x equals to 0. Since this is an iterative process and every iterative process must have some stopping criteria, for the stopping criteria, let us assume that epsilon is my positive integer, which is very small. Then for the stopping criteria, I have two choices. Choice number 1 says after each iteration check the inequality mod of xn minus xn plus 1 is less than epsilon or not. If this inequality is satisfied, then the iterative process will stop and the convergence of the sequence is reached. The choice number 2 says to check if f of xn is less than epsilon or not. If this inequality is satisfied, then we can say that root have been achieved up to the desired accuracy. Let us understand this method with the help of an example, which says to determine the root of x cube minus 7x plus 2 is equals to 0 in the interval 0, 1. We are given that f of x is equals to x cube minus 7x plus 2 is equals to 0. The fixed point iteration method says to rewrite this equation in the form of x is equals to g of x, then use that value of g of x to start the iterative process and check the stopping criteria at every iteration. So I can rewrite this equation as 7x is equals to x cube plus 2, and this can be rewritten as x is equals to x cube plus 2 divided by 7. This method also says to take an initial guess from where the iterative process can start. Since we are given the initial interval as 0, 1, so we have to take the initial point between this interval only. Taking the initial point as x naught is equals to 0.3. Starting the iterative process, the value of x1 is equals to g of x naught, which is equals to 0.3 square plus 2 divided by 7, and its value is 0.2896. Checking the stopping criteria, x1 minus x naught is equals to 0.0104. Here I am taking the epsilon value as 0.001. This inequality is not satisfied, so we will move to the next iteration, where we will find the value of x2 as g of x1 is equals to 0.2892, and here x2 minus x1 mod is equals to 0.0004, which is less than 0.001, implies root of x cube minus 7x plus 2 is equals to 0 is 0.289, correct up to 3 decimal places. From this example, we can notice this thing that if the initial interval was not given and we take initial point as x naught is equals to 10, then the sequence of points xn will not converge. So from this example, we have made an understanding that any initial guess will not work for this method to converge. Moving to the second example, we are given that f of x is equals to sin x plus x square minus 1 equals to 0, and the fixed point iteration method says to rewrite this equation in the form of x is equals to sin x. So I can rewrite this equation as sin of x is equals to 1 minus x square. Finding the value of x here, we can say, and it can be rewritten as x is equals to sin inverse of 1 minus x square. And I have one more choice to write it as x square is equals to 1 minus sin x, Rewriting it again, this can becomes x is equals to plus minus under root of 1 minus sin x. From the equation number 1, I have the possible choice of g of x as sine inverse of 1 minus x square. But from equation number 2, the choice of g of x is under root of 1 minus sin x. Let us see what happens when I take the choice of g of x as equation number 1. Considering it as case number 1, where we let x is equals to g of x as sine inverse 1 minus x square. Since the initial interval is given as 0.1, I can consider any initial guess between this interval. Taking x naught is equals to 0.8 as initial point, starting with the iterative process, x1 is equals to g1 of x naught, whose values is 0.3683. Checking for the stopping criteria, x1 minus x naught is equals to 0.2684, which is not less than 0.001. So moving to the second iteration, which gives the value of x2 as g of x1, which is equals to 1.0439, and the value of stopping criteria is 0.4072, which is again not less than 0.01. Moving to the next iteration, the value of x3 becomes minus of 0.0899, and the value of stopping criteria is 0.7266, which is again not less than 0.001, and the value of x4 becomes 1.4436, and the value of stopping criteria is again not less than 0.001. The fixed point iteration method says that for the iterative process, the sequence we will create of the points x n's must converge. If this sequence will converge to some point, then the distance between the points should be decreasing. But when we notice the stopping criteria, the values are rapidly increasing, which clearly means that this sequence will not converge. Implies when we will take equation number 1 as choice of g of x, the fixed point iteration is not converging to a unique root. Let us try for the case number 2, where we will let the choice of g of x as equation number 2, which is under root of 1 minus sin x. Taking the initial guess as x naught is equals to 0.6, starting the iterative process, the value of x1 be g of x naught, which is 0.6598, and the corresponding stopping criteria be 0.0598, which is not less than 0.01. Similarly, doing all the iterations, it is clear from the stopping criteria that the sequence of xn is converging. Therefore, the sequence xn is converging, and it converges to x is equals to 0.6 as the approximated root of the given function, correct, up to 1 decimal place only. So from this example we have understand that any choice of g of x will not work. The question here arises is, what should we take the value of g of x so that the fixed point iteration method definitely converges? For that, we have a theorem which says if g of x obtained by rewriting the given function f of x equals to 0 as x is equals to g of x should be continuous on the given interval ab, and g of x value should lies between the interval ab for every choice of x obtained from the same interval. Then g has at least one fixed point in the interval ab. Further, the theorem says if the derivative of the function exists on the open interval ab and there exists some positive number k such that the maximum value of derivative of the function g of x should be less than k, where the value of k is less than 1 for every choice of x from the interval a comma b, then we can say there exists exactly one fixed point in the interval a comma b. Let us understand this theorem again. For the manipulated function g of x, it should be continuous and it should map the interval ab onto itself. Then we can say that g has at least one fixed point in the given interval ab. In addition, if its derivative exists on the same interval and the maximum value of the derivative of that function is less than 1 for every choice of x from the interval ab, then there exists exactly one fixed point in the interval ab. Let us make an understanding of this theorem with the help of an example, which says the equation x cube plus 4x square minus 10 is equals to 0 has unique root in the interval 1 comma 2. We are given that f of x is equals to x cube plus 4x square minus 10 is equals to 0. For the fixed point iteration method, we have to rewrite this equation. Let 4x square is equals to 10 minus x cube, which can be written as x is equals to plus minus under root of 10 minus x cube whole divided by 2. Let us mark this as equation number 1, or we can also rewrite this in the form of x cube plus 4x square minus 10, and we add and subtract x and rewrite in the form of x is equals to x minus x cube minus 4x square plus 10, and marking it as equation number 2. This equation can also be manipulated in the another form, which says x cube is equals to 10 minus 4x square. Dividing both sides by x, this becomes 10 by x minus 4x. Taking square roots both sides, this becomes plus minus under root of 10x minus 4x, marking it as equation number 3. Or we can also rewrite as x cube plus 4x square is equals to 10. Taking x square common, dividing both sides by x plus 4, and then taking square roots both sides, which becomes my equation number 4. From this equation, we have manipulated in 4 different forms. Let us check the validity of the above theorem we have stated in every possible choice for g of x. In case number 1, let us take the value of g of x as under root of 10 minus x cube divided by 2. Taking the derivative, it becomes minus 3 x square divided by 2 into 10 minus x cube to the power minus half. Taking mod both sides, this becomes 3x square by 2 into 10 minus x cube to the power minus half. Since we have to maximize this function and the given interval is 1 comma 2, the maximum possible choice for x is 2. Using that value, this becomes 3 into 2 square by 2, 10 minus 2 cube to the power minus half. This becomes 3 into 2 to the power minus half, whose approximated value is 2.121, which is not less than 1, implies this choice of g of x will not work for the fixed point iteration method. Moving to the case number 2, let x is equals to g of x as x minus x cube minus 4x square plus 10. Let g of 1 is equals to 6, which does not belongs to the interval 1, 2. Interval 1, 2 implies the theorem again fails, and this choice of g of x will again not work for this method. We can also find the derivative, which is equals to 1 minus 3x square minus 8x, taking mod both sides, one minus 3x square minus 8x, which can be written as less than equals to mod of 1 plus mod of minus 3x square plus mod of minus 8x, which is equals to 1 plus 3x square plus 8x. Since the choice of x is from the interval 1, 2, implies this value is also always going to be greater than 1. We can use either this or this equation to fail this choice of g of x. For the case number 3, let us consider x is equals to g of x as under root of 10 by x minus 4x. Let g of 1 is equals to under root of 10 minus 4, which is equals to under root of 6, whose values is approximately 0.4495, which is again not contained in the interval 1, 2. So again the theorem will fail for this choice of g of x. For the last case, let x is equals to g of x is equals to under root of 10 upon 4 plus x. Finding the derivative of this function, this becomes minus 5 divided by under root 10 into 4 plus x to the power 3 by 2. Taking mod both sides, this value becomes 5 upon under root of 10 into 4 plus x to the power 3 by 2. Since the value of x is in the denominator, larger the value of denominator, smaller will be the whole value, and smaller the value of denominator, larger will be the value. So here we will use the value of x as 1, not 2, because the minimum possible choice for x in the interval 1, 2 is 1. After solving, this value will become approximately equal to 0.15, which is less than 1. So this choice of g of x will work for the fixed point iteration method to converge. Compiling this lecture, we have firstly seen what is a fixed point, then we have seen its graphical representation. After that, we moved to the fixed point iteration method, which says to rewrite the given equation f of x equals to 0 in the form of x is equals to g of x. Then we take the initial guess and start the iterative process. Then we have considered one example from where we have understand that any initial guess for x naught will not work, and after that we have seen any choice of g of x will not work. Further, we have seen a theorem what conditions the function g of x must satisfy for a fixed point iteration method to converge to its root. Then we have seen another example where we have tried to understand this theorem. I hope you have made an understanding of this method. If you still have any doubts, please let me know in the comments. Keep learning.